And I'll start with a baby example, what I would mean by taking by limit theory. So this is very basic, but I want to illustrate the philosophy of this field. So suppose you look at graphs, and the only one parameter that interests you is edge density. So given a graph G, its edge density, by definition, you take number of edges and divide by total number of pairs. So it would be like V of G is number of vertices. And if you take V of G choose 2, you just count total number of pairs, and this is the edge density. So it's some number between 0 and 1. And then you say two graphs look similar if they have the same edge density. So your distance between two graphs, H and G, in this baby example, is just how their edge densities differ. Of course, it's a very basic example. And now, as I told you before, so what is the philosophy? So we have some notion of similarity between two graphs, and then we express as a distance in this case, and then we take completion. So basically, for every Cauchy sequence, we add extra point modulo some equivalence, and this completion I'll call it limit space lim. And so in this particular case, completion will be, you can identify it with interval 0, 1. And then if you have a graph G, then it corresponds to a point in this limit, which is edge density. But of course, here we look at finite graphs. So what you get would be some rational number. So, and in this baby example, it illustrates this idea that you start with discrete objects, but at the end you get an analytical object like interval, and it makes some statements, intuition, in some cases much easier. Like, for example, you might have like some graph theory problem where the answer, like some optimal edge density, is like irrational number, 1 over square root of 2. Then if you just work with finite graphs, there isn't like an extremal solution. You always have a better and better example. But if you work with the limit, you can pinpoint this optimal edge density right away. So that's the philosophy. So my structure will be, there will be 3 lectures. First lecture today, we'll talk about dense graph and graphons. Tomorrow, I want to switch to bounded degree graphs and graphings because our TA, Riley, he expert on graphings and he proved many beautiful results. So I wanted him to talk about graphings on Thursday. And then on last lecture, I'll try to present some applications of both graphons and graphings. So before I continue, so let me just look again at this baby example. Okay, some question. Yes, so okay, I said distance. So let distance mean a pseudometric. So I'm allowed two graphs to be distance 0, just to make life easier. But in many practical situations, yeah, it will be the case that some graphs will be identified. And so when I say distance, that it means pseudometric. So in this particular example, what we interested in, one way to look at it is to say we sample two random points from a graph, and we ask, do we see an edge or not? And for graphons, there is a similar idea. You sample a k bounded number of points, and you are interested what kind of graphs you see. And then a large part of extremal graph theory would ask what are relations you can prove between these numbers, between these densities. So I want to move to the next topic. So I want to talk briefly about densities. So there are many different ways how you define what a density of a graph is. So I'll use so-called homomorphism density. Because this will be the one which will be most convenient in this setting. Okay, so here, what is a space in which we work? So we look at all finite graphs up to isomorphism. This is my Kelly G. So you can enumerate them in some order. Single vertex graph, empty graph on two vertices, graph on two vertices with one edge, then three vertex graph with no edges, with one edge, and so on. So you have this countable set. Yeah. And given two graphs, F and G, usually the way you should look at it, F is small graph and G is like huge graph of order going to infinity. We want to consider how frequently F appears in G. So if I have some function F from the vertex set of F to vertex set of G, okay, let me just move to new page. Then this map is, I'll call it homomorphisms. By definition, if it sends edges to edges. So if I write it briefly, if I take any pair of adjacent vertices in F, then it's sent by F to a pair adjacent in G. I'll give you an example in a moment. Then I call it, and often I would abbreviate it as just hom when I write it. Then I call it injective homomorphism. If it is a homomorphism, and as a function is injective, which means it sends no two vertices to the same vertex, and I call it induced homomorphism. If additionally it is injective homomorphism, and additionally it sends non-edges to non-edges. So I'll write it like this. So if I look at edges which are in the complement of F, so F bar is complement, then every non-edge is sent to non-edge. So in other words, an induced homomorphism is a map from your graph, which is a isomorphism on its image. So it has to send edges to edges, non-edges to edges, to non-edges, and it's not allowed to glue vertices.
Олег, я вибачаюся, там було питання від Каміла.
Are all the graphs simple, so without loops and multiple edges?
Yes, so for this talk, all graphs are simple. We don't allow multiple edges, no loops. And in the moment, all of them are finite, unless I tell you otherwise. Thank you. Then I have these three notions. So I want to define corresponding counts. So I want to count such maps. So maybe I'll write it on the map in one line. So if I count homomorphisms, I write it hom fg. So this is the number of homomorphism. Then if I count injective ones, this would be injective fg. And if I count induced ones, I'll denote this number by induced f of g. And so maybe let's look at one quick example. Oh, I see one more. Okay, there was a question. I guess the question was about, oops, about right-hand side being edges of G complement. Oh, yeah, you're right, yeah. So yeah, we wanted to say that every non-edge of F is sent to non-edge of G. Yeah, and so here's just some easy example. And Riley, if probably might he do more. So suppose like just pk is path on k elements, k vertices, like here's example p3. Km would be a complete graph on m vertices. So k3 is say triangle. So if I look at a homomorphism of say p3, k3, then okay, if I embed them in say in this order 1, 2, 3, then I have like 3 choices for the first vertex, 2 for the second. It has to be neighbor of the first, so it cannot go to the same. And for vertex number 3, I have again 2 choices because I'm allowed to send 2 and 3 to the same vertex. But on the other hand, if I count injective homomorphism, then okay, for first 2 vertices the same number, but for the last one I have no choice whatsoever. And if I count induced one, well, they have the same number of vertices, so it has to be isomorphism, but these graphs are not isomorphic, so it's 0. Okay, so I defined you like many densities. So in some sense, they are equivalent to each other. So if in some unknown graph G, I know, say, induced densities, I compute the others and vice versa. So let me quickly write these formulas. So for example, how I can compute, say, injective homomorphisms if I know induced homomorphisms. Okay, so let's just recall what is injective. I look at maps from F to G, and I ask that every edge of F is mapped to every edge of G. I might have some extra edges. So it's disjoint union, what extra set of edges I add. So it's trivial identity. So it's equal sum of graphs F prime, which have the same set of vertices as F, but have some extra edges, perhaps. Of an event is that f prime is exactly what I see on the image of this map, little f. Yeah, and kind of later we'll see similar formulas. So instead of writing all these conditions, I'll just write briefly f prime is a superset of f, which means they are graphs on the same vertex set, and every edge of f is an edge of f prime. So this is just trivial relation. And now, well, can I find converse? So in a way, if you look at it, then this is a linear map. So if you imagine G is a known graph, and for every little f you have this vector which counts, then somehow I have some linear transformation which transforms one vector to the other. And if you, for example, order all graphs by increasing number of vertices, then this linear transformation is upper triangular matrix. So you can find inverse, but in fact, here it's very easy to write inverse. And it be a special case of so-called Möbius transformation or Möbius inverse. So suppose I have some function, like counting some homomorphic copy of a graph from a finite graph to real numbers. And the Möbius inverse of this function is equal, okay, so I'll follow notation from book by Lovas. This is the book which I would highly recommend if you want to learn this topic in detail. And in the handout, I gave some link to this book. So, okay, so it's a new parameter. And on a graph, say capital F, by definition, I take a sum over all f prime superset f, which exactly means what I wrote above, that it has the same set of vertices and at least as many edges, and the same edges that F plus perhaps extra edges. And transformation is, I will take -1. I see what is the difference of edges between them. And then I compute f of f prime, little f of capital F prime. So that's definition. And here is our first lemma, which says if I want to compute induced densities of f in some graph G, then I can just take injective home densities, non-induced ones, and apply Möbius inverse. Maybe to be more precise, yes, so this is my function on graphs, where in the second place I can put any graph G. And then if I want to compute it not with injective homomorphism, I just apply this formula. Yeah, and there are many proofs. One which I just mentioned is linear algebra. You can just formally verify this identity. Another way, you can apply some inclusion-exclusion, because basically what we want to do, we look at homomorphism from F into some graph G, but we want no extra edge to be mapped to an edge. So for every pair which is not edge of F, you can define extra event that it's not mapped to an edge. And then you're talking about union of these events. So you can also, one possible proof is inclusion-exclusion. So maybe just let me write one example of this lemma to one. So suppose we look at just very quick example. We want to find induced density of, say, path in some big graph. Then by this formula, we have like two choices for f prime. We can put this extra edge or not. So first, if we don't put it, then we just count injective homomorphisms. But of course, we overcount those maps where this extra pair happens to be an edge. So we have to subtract it. So we have to subtract exactly number of homomorphism of triangle into your big graph. Yeah, and in general, you have similar alternating formula from inclusion-exclusion. And even more general, like this Möbius inverse, it's like very general result which apply when you have lattice and you have some kind of two functions which are related by sums like this on top one. Then Möbius inversion allows you to find inversion of this transformation. Good. Any questions? So somehow I wanted to define maybe this strange notions of copies of F in graph G, because this will be the ones which will be most useful in the limit theory. And in this lemma to one shows basically the day equivalent, at least induced and injective.
Олег, я вибачаюся, там від Валерії Котельникової є запитання в чаті. Does the path have the same number of vertices as F in notation?
No. If you look to graphs, they don't have to have the same number of vertices. I'm not sure to which, here in this example, they just happen to have, because I wanted to have two small examples. Do you refer to this?
No, it's to the lemma. So you write in the lemma, first graph is F, and next one you just like a line. What is this line?
So you mean this one, right?
Yeah.
So this line says the following. So I view left-hand side as some function on graphs. So given, so basically, let me just use different color. So what I mean by this, I mean it's a function given some graph G. It computes induced homomorphism dense number of induced homomorphism from F into G. And then, and I want to write some formula. Suppose I know only non-induced densities, which is this right-hand side. And then lemma says, well, you just to have applied this formula, which is a star. So it's the same F in both parts of lemma to 1. And this identity is true for every graph G.
Okay, got it. Thank you.
Yeah. Mhm. Yeah, and similarly, if you want to pass, for example, between injective and non-injective versions. So for example, let me just one write example. Suppose we look at number of homomorphism. So we map edges to edges, but some vertices could go to the same vertex. How can I compute it if I know only like injective version? Okay, so first I just look at all injective maps. So I captured some maps, but not all. So what happens, there are still more homomorphism which glue some vertices together. In this case, the only possible pair which you can glue are these like two degree 1 vertices, or all three of them. So to compensate, you need to add extra term where you glue two of them together. But there are like three possibilities which two of them are glued together. So you need this factor 3. And also one extra possibility is that like these three vertices, they are all mapped to the same vertex. So final correction term, you add injective from H to G. So that's one formula. If you know injective homomorphism numbers, you can compute non-injective one. And then there are some similar formula how you can do converse. So maybe I won't write it, but it's possible to write it. So what I wanted to say, so I defined three kind of counting parameters, but in some sense, up to some transformation, they're all equivalent. So if you know one of them, then you basically know the other two. So that was the takeaway message from this part. And now, finally, I want to look at the densities. Or homomorphism densities. Suppose my graph capital L F has k vertices. So then basically I want to take a random map and ask what is probability that it's a homomorphism. So for home is denoted TFG. So how many maps do I have? Here, if you remember, I allow vertices to be mapped to the same vertex. So my scaling factor would be n to the k. Each of the k vertices of F has n choices. And I ask what is the probability that random map is homomorphism. So I take all homomorphisms and I divide by possible number of maps. And then similarly for injective homomorphisms, again, you ask what is the proportion of maps which are injections that give you homomorphism. So the scaling factor here would be falling power of n. So let me write definition immediately. So how many injective maps do you have? N times n minus 1 times n minus 2 and so on. You have k terms. So the last one is n minus k plus 1. And we just ask, what is the probability that injective map is homomorphism? Of course, to make sense here, we have to not to divide by 0. We have to assume that n is at least k. And finally, induced density of f by definition. So these are all definitions. Is you take injective map and you ask what is the probability it sends every edge to edge and every non-edge to non-edge. So somehow you can view it as people call it densities, or you can view it as frequencies of f in your big graph G. Any questions? Yeah, I know there are lots of definitions. Hopefully we'll start soon proving theorems. So maybe again, quick example. So if I looked at density of non-induced one of paths, say in a triangle, well, I have 3 to power 3 different maps. And from previous example, we know how many so many of them are homomorphism. So the answer would be whatever 4/9. But if I look, let's say, injective density of a path in a triangle, then number of injective maps is 3 times 2 times 1. And here number of homomorphism is the same. Well, every injective map is homomorphism. It has to map edges to edges. So here the answer is 1. So just because of scaling, here we agree that injective home density of path in this case is 1. And non-injective is 4/9. And this would be convenient to have different scalings for these two problems. Yeah, if you read some literature, especially on so-called flag algebras, you notice that people often use a different notion of densities. So what they do, they take a random k-set inside your big graph G, all sets being equally likely, and you ask what subgraph it induces in G, and you ask how likely is to be isomorphic to F. So again, we have two graphs. F has k vertices. In a bigger graph G, we pick random k set, see what edges are inside. So it defines some graph with k vertices. And then we ask how likely is to be isomorphic to F. And this is often appears in papers. So in this case, you can easily compute it from induced density. Maybe one way to do the following: if I have a k set which makes a copy of F, then there are k factorial bijections. But some copies, if I have F has symmetries, so some copies of F are overcounted. So I have to divide by number of automorphisms of F. So there is this relation. So basically you can say, if I have a set X, which spans copy of F, how many homomorphism does it give? So potentially I have like So for each, so every homomorphism gives me a k-set. So a k-set could be counted k factorial times potentially, but then I overcount its number of times, which is number of symmetries of F. Yeah, so maybe it's kind of calculation. Sorry if I failed to explain it. If you just sit at home and carefully write both sides, yeah, that's something you should get easily. Yeah, and now, so having defined all these densities, yes, so I'm ready to define a notion of similarity on graphs or notion of convergence. So this will be our third section. Yeah, so somehow, okay, so you have sequence of graphs and we want to define when they converge. And informally definition is that we want the graph to be similar to each other if they have similar frequencies of subgraphs. So the edge densities are close to each other, triangle densities, path densities, and so on for every graph. And then a sequence will be convergent if basically these statistics converge for every f. So when I write Gn, I would mean just some sequence of graphs indexed by integers. And maybe to avoid some technicalities, I always assume that number of vertices increases. So whenever I write a sequence Gn, it means a sequence of graphs with a larger and larger number of vertices. And then a definition. So a growing sequence of graphs converges. And then okay, and this limit object, I'll denote phi, and be clear in a moment. So by definition, if for every fixed graph f, so it's finite simple graph, if I look at a sequence of densities of capital F in Gn, so this is just sequence of some numbers, each one between 0 and 1, if this converges. And phi is just function of graphs which gives this limit density. So again, so when I consider sequence of graph convergent, if I take, say, triangle, and I see how many triples of set span triangle, what is the fraction? Maybe it's like, then this should be, as n increases, this fraction should converge to some number. Yeah, and in these definitions, yeah, you can use any other of these parameters. So you can use T injective, is the same, or you can use induced version, except then if you use induced version, this limit would change to a different value, but convergence will still be true. So if you don't care about 5, then you can use also induced density to be a bit different limit, but you can compute it given other limits. So maybe let's look at some examples. So suppose I take sequence of complete graphs on n vertices. So what is my function phi? Well, if I take any f and I map it to a larger and larger clique, and larger kn, then, well, very likely all vertices go to different vertices. It's injective. And then since it's complete graph, it sends edges to edges. So the limit is 1 for every f. So if I have a complete graph on n vertices, then the limit as a function on graphs is identically 1. For example, suppose I have a sequence of graphs Gn such that, let's say, each one has a small number of edges. Let me just try. Such that number of edges in Gn is a little negligible fraction of total possible number of edges, which is number of vertices squared. Then every such Gn converges. So what is phi? So I have my f. Well, if f has at least one edge, then I send this pair to a big graph Gn, but it's essentially empty. So very likely this edge is mapped on an edge. So I don't have homomorphism. So the limit will be 0 if f has at least one edge. And finally, if f is the empty graph, no edges, then limit is 1. Well, for empty graph, yeah, it's homomorphism density in every other graph is 1. And yeah, maybe one more example or rather a definition. So a sequence.
Sorry,
Yeah.
we have a question from
Yeah.
Alexei Goldanov on the chat.
Yeah, so that was a good question. So if this phi is arbitrary, yeah, it's a very good question. So not every phi can come as a limit. So I'll give you a few different characterizations, hopefully later in today. So I would write exactly which properties phi have, and these properties will characterize all possible limits. So it's not any function is possible. So there are some consistency conditions which have to be satisfied. And so here's definition. So a sequence of graph I call, say, P quasi-random. If it converges.
Sorry, you said at least one. That should be greater equal or strongly greater.
Oh, great. Equal. Thank you. Yep. If it converges to a function phi, maybe I'll call it phi little p, which by definition is you take a p and to power, which is number of edges in f. So for example, if you take f a triangle, then it means you have like p cubed triangles. If f is like path, say, on two edges, then density of paths should be p square. And one example is maybe just stated as a lemma. You can wonder if such graphs exist. So that will be lemma 3,1. So if you take any probability p, any real number, and you look at so-called Eddy-Shreni random graphs, so I'll denote G and P. I'll write a definition in a moment. Is P quasi-random. Okay, so these are random graphs. So this is some event which may happen or not, but this happens with probability 1. And what is G and P? So it has n vertices. Vertex set is, say, consists of integers 1 to n. Yeah, and I'll denote such set as bracket n. And what are edges? So for every pair ij, I make it an edge with probability p. And all choices are independent. So you have n choose 2 pairs. So for each one, you throw a biased coin, which comes heads with probability p, and you put this edge if it comes head. And then, so yes, so indeed, like this phi p, it's possible to realize by finite graphs. Yeah, and then there is nice theorem by Chan Graham Wilson. So I'll call it theorem 3.1, which one of the 2 papers that started this study of quasi-random graphs. Proved in 89. It says the following: if you have sequence of graphs. Okay, so this definition of quasi-randomness, for every f, its density should satisfy this condition. We roughly repeat the number of edges. But Chan Graham Wilson theorem says, well, for this, it suffices to check only 2f, h and for cycle. So it says if density of h in Gn is p plus o little of 1, and the home density of for cycle in Gn as n grows is again what we wanted, p4 plus arrow term that tends to 0. Then this Gn is p quasi-random. So this famous theorem, yeah, maybe in lecture 3, I'll try to sketch you a proof. And at least give you some partial motivation for going through all these long definitions. So here is like a limit version of this theorem. So if I want to state it in terms of limits, then basically statement, I think is very clean and nice. It says if you take every limiting function phi, and it happens to have correct values at h and at for cycle, then for every f, phi of f is whatever comes from definition of quasi-randomness, p to power number of edges. So there are no arrow term. We don't have to talk about sequence of graphs. We just say take any limit object, phi. And then if h and for cycle have correct densities, then phi is quasi-random. I haven't defined what lim is, so let me define it. So what is a lim? So I can see all functions, okay, which take input finite graph and produces some density, which we know is some number between 0 and 1, such that there exists some finite sequence of finite graphs, which converges to phi. Okay, so that's definition. Let me maybe separate it from here. So basically, what is lim? Well, it's some functions on graphs. So it's some subset of 0, 1 0, 1 valued functions on graphs. And if you look at convergence, we say for every f, values should coincide. So this is exactly pointwise or product topology with pointwise convergence or product topology. And then one of the homework exercises, just by definition, it follows, it has to be as a subset to be closed. And this total product space is compact by Tikhonov theorem. So this, just by definitions and these theorems as black boxes, it's a compact set. So one consequence is, which I'll call lemma 3-2. So if you take any growing sequence Gn, then it has a convergent subsequence. So its lim lives inside compact metric space. So if you take any infinite sequence, it has accumulation point. Or this lemma you can just prove directly, because if you have sequence of graphs, you can apply this diagonalization process. So you look, for example, density of K2, you pass to subsequence where this density is converged to some number. Then you look at next graph in some fixed order, say path with two edges. Again, by passing to subsequence, you can assume that this converges to some number and so on. And then you just diagonally go among these subsequences. Good. So, yeah, so that's the limit space. But so far, we didn't use much of the theory. We just defined it limit space as just formal functions which give you limiting densities. Let me make you a few more observations before we move to graphons. So one observation is that every graph G I can map to some point in this limit space. So I'll call this point phi of G. And this is limit of the, when I take my graph G and I blow it up uniformly. So this means M blow up. So maybe just give me an example. So here is my path of length 2. What would be like blow up of this path? Well, each vertex are replaced by set of size M. And then if I see an edge in my graph, I put all possible M square edges here. So this has a size M. Here I put M square edges. Whenever I see an edge, I have a second edge. So I put another complete bipatted graph. At the base horizontal part, I don't see any edge, so I don't put anything. So this blow up of a graph. And a nice property, that's why I like this density T. So if I take any F and look at its density in G, it's exactly a density of F in any blow up of G. Because the way, if you think about what happens, say, in left-hand side, I have my little graph F. Every vertex is sent to a random vertex of G. And left-hand side is probability that I see edge whenever it's an edge of F. And with repetitions, it's non-injective map. And the right-hand side, again, I map it to a bigger graph. But since all vertices are replaced by M sets, then probabilities are the same. Yeah. And then there was question earlier in the chat, which phi are possible. So let me state some properties of phi, and then I conclude maybe with theorem that these are sufficient. So what are properties that every limit has to satisfy? So one trivial property that it's normalized. And means if I take phi and evaluate it on a graph on one vertex and no edges, then it's always 1. Then another property is multiplicativity. So phi is multiplicative, which means if I take any two graphs, so when I write them next to each other, I mean a disjoint union. So I have two graphs. If needed, I relabel vertices in the second graph to make it disjoint from the first. And I just take a disjoint union. So now if I want to find density of disjoint union, since I allow repetitions, I can map first graph any way I want, and independently I can map a second graph any way I want. So this will be product of two densities, because probability of two independent events is the product of two probabilities. And then last property is that if I take upper Mobius inverse of phi, using this formula we had before, it's non-negative, because if I take any f and I compute upper Mobius inverse on my graph f, well, so limit, so upper Mobius inverse, it was some finite linear combination, so I can exchange it with limit, and phi was a limit of some graph, say Gn. So I have to compute this quantity inside Gn. But then I know what is this. Well, by this lemma, it's exactly is roughly its induced density. So Gn growth, so this T is the same as injective density, and by upper Mobius inverse formula is the same as induced density.
Oleg, and we have some comments from Alexei Gaidano. Please see chat.
Yeah. Yeah, so the question was about definition here of this phi of G. Yes, so I take limit of blow-ups of G as this M goes to infinity. So I take big and big blow-ups, but each vertex is blown up the same number of times. Yeah, and here, okay, so it's a limit of some numbers, but each number is non-negative. So yeah, limit is also non-negative. And let me just finish with this theorem by Lovász and Szegedi, that actually these three properties exactly characterize possible limits. So they proved in one of the very first papers on graph limits that suppose I have some function on graphs into reals. Then this phi is a limit of finite graphs in the sense I described above, if and only if the above three properties hold, if it's normalized, multiplicative, and if you take its upper Mobius inverse, then it's non-negative on every graph F. And maybe just to say briefly about, so one direction we just showed, that these two properties are necessary. And to prove conversely, somehow that's probably I'll do either on Friday when or I'll decide what I'll do. So to prove converse, you have to define how, given a function phi, how you can generate so-called random samples from phi, and then prove that with probability 1 they converge to phi. So it's not a proof. The other direction is not quite trivial. It requires quite a work. So, so maybe I'll discuss it next time. So I'll stop today here. One last remark. So problem 5 on the homework, it assumes you know what graphon is. We didn't get as far as that. So just homework for today will be only problems 1 to 4. So problem 5, hopefully after Wednesday class, you'll be able to work on.